Take a look at a standard socket wrench. That mechanical click tells you the tool is locked in one direction and free in the other. It is a simple piece of hardware, but for over a century, physicists have used this exact mechanism to try and find a loophole in the most unbreakable laws of the universe. The engineering relies on a geometric trick. The wheel is covered in asymmetrical teeth, a shallow ramp on one side and a steep face on the other. A pawl slides easily over the ramps, but jams solid against the steep faces, blocking backward motion. Now imagine shrinking this tool down to the size of a single molecule. At that scale, you don't need a hand to turn the wrench. The air itself is a chaotic swarm of molecules, constantly colliding with everything. Attach a microscopic paddle wheel to this gear in a chamber of gas, and random molecular impacts will strike the paddles. Since the ratchet blocks reverse motion, forward bumps move the wheel, while backward bumps are simply ignored. In theory, the wheel should spin forever. You would be pulling usable work directly out of ordinary room temperature heat, creating a machine that generates infinite energy from nothing but thin air. Marian Smoluchowski, a prominent theoretical physicist, presented this puzzle to his colleagues in 1912. He didn't frame it as a fantasy, but as a genuine contradiction in the math of how energy moves. This device belongs to a specific category, a perpetual motion machine of the second kind. Unlike a machine creating energy from nothing, this pulls existing energy out of a single environment, turning it into motion without any waste. For decades, the puzzle sat unsolved. On paper, there was no obvious reason why the ratchet shouldn't just keep spinning, powered by the jittery heat of the atmosphere. If this machine could actually function, it would mean that our understanding of thermodynamics was incomplete. It suggested that under the right conditions, the law of entropy could be bypassed. In 1962, Richard Feynman took up the challenge to analyze the mechanism not as an abstract idea, but as a physical piece of microscopic engineering. He modeled a complete apparatus, a gas-filled box for the paddle wheel, a shaft connecting it to the ratchet and pawl, and a tiny weight on the end of a string, ready to be lifted by the molecular motion. At this scale, traditional engineering fails. You cannot use standard hinges or pins, because the friction between the parts would be enough to lock the entire machine in place. Modern solutions use compliant mechanisms, parts that don't rub against each other, but instead bend as a single solid piece. These flexural pivots use the material's elasticity to act as both joint and spring. But even these joints have a limit. Hammered by microscopic impacts thousands of times a second, the constant vibrating and bending leads to rapid material fatigue, causing the flexural pivots to snap. Feynman realized that even if you had a perfect, indestructible material, the machine still wouldn't work. The problem wasn't the engineering, it was the atoms themselves. The flaw is that the pawl is also made of atoms, and at any temperature above absolute zero, those atoms are never still. They are vibrating with their own internal heat. Because of its microscopic size, the pawl's thermal jitter makes it bounce. It vibrates upward, lifting off the locking tooth just long enough for the gear to slip backward. The heat pushing the wheel forward also shakes the gatekeeper out of position. Feynman's math proved that if the gas and the pawl are at the same temperature, the forward pushes and backward slips cancel out exactly. On average, the paddle wheel goes nowhere. This is the same reason Maxwell's demon, a hypothetical creature sorting fast and slow molecules, can't work. The gatekeeper is always part of the system it's trying to control, and it eventually gets shaken by the same chaos it's trying to filter. You cannot use random motion to create order for free. The energy simply balances out, and the system reaches a stalemate. Feynman did find one way to make the system move. You have to keep the pawl colder than the gas around the paddle. Cooling the pawl reduces its internal vibration. It stops bouncing, which allows it to catch the teeth properly and finally lift the weight. But the moment you require a hot side and a cold side, the magic disappears. The device is no longer a free energy machine. It has become a standard heat engine. This is the exact principle that powers your car. It requires a temperature difference, burning fuel to create heat, and an exhaust system to carry it away, to generate motion. It's the same physics inside a refrigerator, which uses energy to move heat from a cold interior to a warmer room. Every industrial power plant works this way, using the flow of energy from a hot source to a cool sink to turn a turbine. The ratchet didn't break the laws of thermodynamics. It provided a mechanical proof for them. It showed that extracting useful work from the universe always requires a gradient. For 50 years, this was just a thought experiment. But in 2018, physicists successfully built a real molecular version of Feynman's ratchet. They used laser-based optical tweezers to act as the pawl and the gas. The experiment worked exactly as predicted. At equal temperatures, the wheel stood still. With a temperature difference, it began to turn. So the next time you use a ratchet wrench in your garage, just listen to that click. That sound is a mechanical reminder of the second law of thermodynamics in action. It is the universe insisting that every bit of work has a cost and that you can never get something for nothing.